Okay, so back to the photoelectric effect. So the first diagram, the first experiment, evacuated tube, negative electrode on this side, that was a photosensitive metal, positive electrode on the other side, that was the collection electrode. When light shone on the photosensitive metal, electrons were emitted. Those electrons then flowed through the wire, registering a current in the ammeter. When no light was shone on it, no current in the ammeter. As long as the light was above some frequency, FO, the threshold frequency, then electrons would be emitted, but the number of electrons emitted didn't change as the frequency went up. But they did change as we made the light more intense. So as long as the frequency was above some minimum frequency, then the number of electrons increased as the intensity increased, but not as the frequency increased. But what they did notice seemed to change as the frequency increased was the kinetic energy of the electrons. The electrons seemed to move across quicker. The current was being registered in the ammeter quicker. And so they wanted to study it more in depth. And so they changed the setup. And so they took out the power supply, and they put it, which had a set voltage, and they put in one that had a variable voltage. The other thing they changed is this time now they made this it's still a photosensitive metal here, but this time they charged it positive. And they made this guy, instead of it being, they made it negative. So instead of calling it the collecting electrode, this time it was called the stopping electrode. Because now, when I shine light on my photosensitive metal, and little electron dudes come off with some kinetic energy and make their way out into the evacuated tube, now, instead of feeling a force of attraction to this electrode over here on this side, they feel a force of repulsion. And it begins to slow them down. Okay, and so then what we did with the apparatus was we kept jacking up this variable voltage. We kept making it bigger and bigger and bigger, because remember the equation, V is equal to W over Q. So this becomes VO, the stopping potential, and the W is really the kinetic energy of the electrons that are photosensitive electrons that are being released. And so it becomes the stopping potential ends up equaling 1/2 the mass of the electrons times their velocity squared over their charge. I didn't say it on the last video, but the electrons being released are called photoelectrons. And all that means is that they're being released because of the light shining on them. Okay? And so this VO is known as the stopping potential. And remember, I can change it. I can crank it up. It has imagine it as a knob here, right? And I can make it bigger and bigger and bigger. And I have an ammeter here that's going to tell me the effect of me making it bigger and bigger and bigger. So the bigger the voltage, the more negative this plate is, and the more negative this plate is, the more repulsion these little electrons that just got freed from the photosensitive metal, the more repulsion they're going to experience. So when the voltage is low, they get slowed down, but they can still make it to the plate. But as I make the voltage bigger, the slower guys coming off aren't going to make it. Only the fastest ones will. And I can increase this voltage and increase this voltage until finally the reading in the ammeter is 0. And when the reading in the ammeter is 0, then I know that I have just found what's called the stopping potential. And this energy would be the maximum kinetic energy with which the electrons left the plate. And we call it EK max. Okay, because the ones that left with less than that would have stopped earlier. So it tells us that we found the potential that stops the ones with the maximum energy. Okay, so now they wanted to play with the same two variables as they did the last time. They wanted to see what effect will the intensity of the light with a given frequency, what effect will the intensity now have on the number of electrons? So we're going to change the intensity and see what happens with the number of electrons in this particular diagram. Okay, and then, oh no, it's not number of electrons we're looking at this time. What effect does it have on the maximum kinetic energy? We already did number of electrons in the last video. And then we're going to change the frequency. And we're going to see what effect on the maximum kinetic energy of the electrons does the frequency have. Okay, so I'm at a frequency where there's electrons being given off, so I have my frequency constant. Electrons are being given off. And now I'm going to change the intensity and see how that changes the speed, the kinetic energy. And I'll know that by, as I change the intensity, do I have to change the variable voltage to stop it, And the answer is no. The intensity of the light seems to have absolutely no effect on the kinetic energy. But when I do this for frequency, so now my intensity is constant, the brightness of the light isn't changing, but I'm going to change the frequency of the light. I'm going to first maybe shine red and then blue and then green. I'm going to change the frequency. And what effect does increasing the frequency of the light have on the kinetic energy? Well, below a certain frequency, absolutely nothing is given off. And so there is no kinetic energy. But above that frequency, the relationship, the frequency, and the kinetic energy is a constant. And what I didn't say on the last diagram, and I should say here, but it's true for the last setup, the metal is also a constant. So we might be doing this for like copper. Okay, so we haven't changed the metal yet. So they got this straight line. And so then they changed the metal. So maybe this is copper. So then they did it for, I don't know, maybe aluminum. And when they did, they got a similar straight line with exactly the same slope. Aluminum had a different minimum frequency above which it would release electrons, but then the slope was the same. The two lines were parallel. And then maybe they did it with silver, and they got the same slope. And then they did it, okay, so they were like, okay, this is really weird. How come all the slopes are the same? And what is that slope? And whatever it is, it must be important because it seems to be showing up in all these metals. Okay, so let's just recap. So we've changed the apparatus, so now we have a variable voltage, and we've switched the sign, the polarity on the electrodes. So now the one that the electrons are heading towards is the stopping electrode. The one they're leaving is the positive. Now sometimes people will say, but wait, that's positive. That's positively charged. Where are the electrons coming from? Remember that atoms have tons and tons of electrons. The positive negative just means how many excess, but it doesn't mean there aren't any electrons there. So we shine light on it. The electrons begin their journey across the evacuated tube, but now they're experiencing repulsion, and that slows them down. And so as I crank my stopping potential more and more, they slow down more and more until finally there is no electrons entering the circuit. And so we have then that our stopping potential VO is equal to EK max over Q. And so then we varied the intensity and we varied the frequency, and we got these two pictures, but we don't know why. And I hate to tell you this, but that's where I'm stopping. Okay, so I'm stopping here because that's 3 videos today. There's no homework on this. You can work on your practice assignment for mirrors and lenses, and in the next video we'll take a look at why is this happening, and it'll lead us to Planck and Einstein. Okay?